Hello, I'm Seungwon Do from the KAIST. Today, I'm going to introduce my research, Improving Reliability of Virtual Collision Responses, which is about a queue integration technique. Let's imagine that there is a person who is going to hit the ball in the real world. The hand hit the ball exactly at the moment that the person moves the arm. At this time, which cognitive process is working in the human's brain? The internal model gets both impact force and sensory feedbacks as input. So, let me explain about the internal model. Easily speaking, the internal model is a kind of small simulator in the human's brain. The role of this model is estimating something from inputs that have some information. In this case, this small simulator starts to estimate where the ball is going. There is no big difference between the human's estimation and the real result because they already know how it works. So that means people think it's natural. There is another situation, virtual world. Let's imagine that there is a person who is going to hit the ball in the virtual world. When a user hits this virtual ball with their hand, the internal model also works as the same way. But this is not a real ball, so that means there is only limited feedbacks without the impact force. So with this limitation, the internal model is trying to estimate the direction of a virtual collision. Unfortunately, there is a big gap between the estimation and system response about the direction of the ball. That means even though they are in the virtual reality, people adapt to the familiar situation of collision result that they already experienced in real world. So, people usually feel uncomfortable when they hit something in VR. If there is a certain target in VR, the user cannot hit the exact point, so the ball unintentionally goes somewhere. So the result of each accuracy and precision are not good. To solve this problem, basically, we need to consider and bridge this gap between the estimation and system response. First solution is just practice. If users have enough experience for these virtual collisions, they will adapt to this virtual environment over time. Then, their estimation will set focusing on the system response of the physical engine. Or a haptic device will be helpful because it can feel similar to real, so the estimation will also change as well. However, both ways take a long time and require special extra hardware like a haptic device. So in this research, we focus on the inside of internal model by modeling the way of the estimation. We considered how human collision direction is estimated using the internal model and changed the system response in that direction. This new approach suggests the new collision response model using a queue integration theory. The queue integration theory is one of the human perception theory. It provides a statistical model by describing the process that estimates from different sensory channels are integrated into the final estimate. Let me introduce this theory briefly. Guess there is a stick, a normal wooden stick, and we have a task to estimate its length. You can maybe easily touch and feel it to measure the length of the stick. If you estimate it many times with touching, let's assume that the mean of the estimation is 10 cm and the standard deviation, called sigma, is 2 cm as a haptic estimation. How about just seeing the stick without touching and guess the length? In this case, let's say the mean of estimation is 6 cm and the sigma is 2 cm. As a visual estimation. At this time, the queue integration theory is that the explaining process dealing with the final result by integrating both estimation results. In this example, both visual and haptic estimation have same sigma value, which is 2 centimeters. So the final estimation will be the mean of the two estimations, not only focusing on one side. However, what if there are some leaves on the stick? This means that there is a visual noise. In this case, when it touches the stick, it doesn't matter even though there are kind of noise. But in the visual estimation, the sigma will be bigger by the noise. So the result, based on the Q integration theory, focuses on the haptic estimation because the reliability in terms of visual estimation is least dependent. In our case, we decide that humans get orientation and velocity estimation through vision and kinesthetic cue in a virtual collision. So, we calculated the final estimation of the direction of the virtual collision by integrating the orientation and velocity estimation using the Q integration theory. When the hand moves slowly, the user's final estimation relies on the hand normal vector. Because the variation of the hand normal vector is small, then reliability of the orientation estimation is high. While the hand moves fast, the final estimation is more relies on the hand velocity vector because the variation of the hand normal vector is big, then reliability of the velocity estimation is high. As a result, when the hand speed is increasing, the sigma of hand normal vector is increasing, whereas the sigma of velocity vector is decreasing. The final estimation is the result by adding different weight to the hand normal vector and velocity vector by the hand speed. We applied this new virtual collision response model to the system response and set to cause a virtual collision in the direction of the human's final estimation. This algorithm is easily calculated and can be applied to game engines such as the Unreal Engine and Unity. But for this, we have to find 4 free parameters for considering and calculating the perception variance of a human. In study 1, we tested for figuring out these parameters first. For each trial, 3 conditions including direction, speed, and diameter are randomly selected to be hit in the virtual space. A total of 16 participants did hitting a ball task. You can check the video on the right. Also, as shown in pictures, each participant wore a wooden board on their hand in order to unify the contact point between the ball and the hand at once. With the result of data based on study 1, we calculated how the final estimation of collision direction could be similar to the ball condition by these value sets. In the result, we finally got specific free parameter values. That means the final estimation is reliable in the velocity vector when the speed of hand is faster, while it reliable in hand normal vector when the speed is slower than about 1 meter per second. After changing the system response with this new final estimation, we define this as an integrated response and the system response from the original physical engine as a conventional response. So, based on these 2 responses, we experimented at study 2, which is the task of hitting a target using various ball conditions. As seen in the figure on the left of the slide, you can see the 4 balls having different physical material about friction and bounciness for this test. Also, there are 2 different target plates. This is because participants were required to control the speed of the ball hitting the target at 2 levels, faster or slower than 4 meters per second. So for the test, participants tried to hit balls and were required to shoot the ball to the middle of the target as accurately as possible. The result shows different, as shown in the plot from the data of 18 participants. The hitting area of the target plate in the integrated responses shows least spread compared to the conventional response shown. We calculated accuracy through the root mean square deviation of the distance between the target center and these hit points, and got precision through the standard deviation of hit points as well. Most of the conditions shows the integrated response improved accuracy and precision compared to the conventional response. More specifically, there are about 9% improvement in accuracy, 30% improvement in precision. We also evaluated NASA TLX results, and the result shows about 27% better in the integrated response in the performance category. To sum up, we proposed a novel collision technique improving the directional accuracy and precision of virtual collision responses in VR. Our technique did not require any additional hardware and could be directly applied to existing systems. However, we dealt with a low degree of freedom and limited sensory channel. Thank you for your listening. If you have any questions, feel free to email me.